Let's welcome Dr. Sally Thomson to the Modeling Forum at Earth and Environmental Sciences area of Lawrence Berkeley National Lab. This modeling forum, a little background here. This was started more than 20 years ago by Carsten Prus, and that was primarily for tough family of codes we used to discuss. But over the times, like new codes came in and we started inviting people outside the tough community. Well, let's welcome again, and it's 5 p.m. in Australia, so thank you very much for making this time for us. So looks like everybody knows about Dr. Sally Thomson, so I'll make it a brief introduction of her. So Dr. Thomson received her undergraduate degrees from the University of Western Australia. She did her PhD from Duke University in 2006. Then she worked as a postdoctoral scholar at Princeton and Purdue universities. And she joined Berkeley campus, University of California, Berkeley in 2012 as an assistant professor. And in 2017, she was appointed the inaugural Claire and Xie A. Wenshen Distinguished Research Chair. And then in 2019, she moved back to Australia and joined the University of Western Australia. She has also received several awards, including the US National Science Foundation Career Award, the American Geophysical Union Early Career Award in Hydrology, and the European Geophysical Union Jim Touche Award for Best Paper in Hydrology and Earth System Science. So let's welcome her again and take it away, Sally. Thank you.
Okay, thanks, Dipankar. And I'll share my screen now, and we'll just hope that this doesn't cause craziness, because we know this is often the point when things go wrong, don't we? So thanks so much for attending this webinar. And thank you so much for not being offended by my slightly provocative title, which I must admit was originally geared at maybe less of an expert hydrology audience and more of a broad civil engineering audience. In hydrology, particularly in research hydrology, I think it's fair to say that we are often interested in dramatic problems and large-scale issues, whether that be the shortages that I know are plaguing California at the moment, or the extreme flow events. And these are some images from Sydney in March, where they had some extreme flooding. What I want to talk with you about today, though, are not what we do about those really big, consequential, catastrophic events, but rather about some of the modelling practices that are still used for design of infrastructure that handles much smaller scale events. And I hope the Berkeleyites will note that there's a little bit of a shout out to some flooded underpasses in the Berkeley region. And I suspect everybody in Berkeley has their own favourite stories of the stormwater infrastructure failing dramatically. My favourite was walking past Ohlone Park one morning and watching a literal fountain of water coming out of the storm drains. But also not only thinking about the infrastructure that may be undersized or may not cope with the large flows, but also drawing attention to situations where we get our infrastructure wrong in the opposite direction and really oversize what we're building. And there's some examples from Perth, Western Australia, that are shown there as well of oversized infrastructure that just isn't getting the flows for which it was designed and consequently doesn't function all that well. And there's a lot of reasons that infrastructure will fail, and to some extent, as I'll discuss, that failure is by design, in that we don't want to over-design our water infrastructure. There's also bad luck, there's also maintenance, but there are issues around whether or not the initial design that's done in the first place is appropriate and fit to purpose, and the role that the models that are still used for design might play in getting that right or wrong. And so I'm hoping that in looking at what's going to be a profoundly unsexy part of hydrology, the sort of stuff that we teach in classes and that people go on to practice in the field, and thinking about how that can sometimes embed real problems, I'm hoping that might inspire all of us to think a bit more deeply about issues of the connection between research, education, and even governance. Because I think one of the reasons we continue to see not great stormwater design is often that there aren't the feedback loops towards a cycle that produces better functioning infrastructure. So what I'm going to go through this morning is just to remind everybody what the sort of standard philosophy or approach to infrastructure design is for wet conditions mostly. That's going to push us towards reminding everybody about the rational method, which is the method I'm going to tear to pieces this morning, and how it is supposed to work. Then we'll take a bit of a closer look at the timescales in the rational method and the runoff coefficients in the rational method, and then have a bit of a think about where all that leaves the use of this method. So, to some background. When we do design for stormwater, we generally say we can't design infrastructure to remove the risk of flooding or remove the risk of failure. And so our design target is not around the possibility that you get the sort of event that you see in this slide, but rather around how you modify the probability of seeing that sort of an event. So that the first question we usually ask ourselves is, how often should our infrastructure be allowed to fail? And we tend to answer that question probabilistically with a frequency or the inverse of a frequency, which most of us are familiar with as a return period. Now, personally, I think this is the hardest part of any kind of engineering design, because it's not really engineering that determines the return period, but some combination of social, economic, and ethical considerations. So it's really quite hard to say how often you should let things break down. But let's say that we've made that decision, we're ready to move on from the socio-economic ethical stuff and do some hydrology. And so the question that we want to ask, whether we're designing the culvert for Strawberry Creek down at the bottom of Berkeley campus or some other piece of infrastructure, is what are the flow conditions that we expect our catchment to produce for that return period or on that return period? And from there, what are the flow properties that we need to accommodate with our infrastructure? So we usually refer to this as the design flow. And it's really the key thing that's going to inform subsequent engineering design criteria. So we know, again, I don't think this is a surprise to anybody on this webinar, that this is problematic in itself, working out what our design flows are. And what we're saying here is our design flow is some function of our return period, and working out what that function is means that we need to know about the probabilistic behaviour of ideally the flow. And of course, the trouble is that in most of the places where we want to do this small scale sort of engineering design, we don't monitor flow. And so we don't have anything from which to base an empirical statistical approach. And so in general, what we'll do is turn to rainfall, which tends to be a little bit more smooth through space and more widely and more continuously monitored over time. One of the nice things about being in Australia is that we have very nice access to, honestly, easier to use the National Weather Service meteorological data, and the ability to grab these intensity, frequency, duration curves that summarise a national consensus on the statistical behaviour of rainfall extremes across the country. So relating return periods to rainfall is usually the approach that we take. And having done that and acknowledging that there are many challenges with doing that well, particularly for high return periods, we then need to relate our rainfall to our flow. And this, of course, is where hydrologic models come into play, where we may also need to, we may also, if we're being sophisticated, take a second step and acknowledge that the return period of the flow is not necessarily the return period of the rain, bringing us to Monte Carlo type approaches in our models. What I just sort of want to lead with here is that obviously there's a zoo of hydrological models out there, and I have a suspicion that in a research modelling forum, many of the modelers are at the 3-dimensional or 2.5-dimensional, highly distributed end of the spectrum with lots of process resolution, lots of complexity. But that when we're thinking about practitioners, we much more often would see practitioners using lumped models, so semi-distributed models that don't capture with the same fidelity the heterogeneity of our land surface and processes as the 3D guys do. and that it's still quite common in practice to find design being done with even pen and paper type models like the rational method. And this very old, much maligned and yet very widely used method is what I'm going to keep talking with you about today. It's a very silly thing to do some research on as far as publication goes, because 90% of the research community says, oh, that old thing, who cares about that? And 90% of the practitioner community who uses it says, oh, don't touch with our rational method. So I think there's stuff to be learned here, but it's been a bit of a lacuna. To remind those of you who wouldn't go near the rational method if your life was dependent on it, what this thing is, it's a beautifully simple little equation where we say that our flow is proportional to the intensity of the rainfall, the catchment area, and some coefficient that we like to call a runoff coefficient. So you can immediately see the attraction of such a simple mathematical formula. We in hydrology know that this is a highly problematic method to be used. Issues with the rational method that are quite widely promulgated, and the sorts of things that hopefully you do remember from your hydrology classes, are that it's not appropriate for large areas, that it's not appropriate for very heterogeneous areas, and that it really doesn't capture the full complexity of the runoff generation process. How could it? It's three little numbers multiplied together. So we know we shouldn't be using it, but we do use it. So here's a very brief survey of just research literature and looking at number of papers published that refer to the rational method in one way or the other. And what we see is that this has been growing over time. And you might say, well, look, that's just that publications have been growing over time. But when you normalize this, we actually find that in the last 5 years, about 5% of hydrologic publications in the literature actually refer to the rational method. So this is not a trivial amount of work or a trivial prevalence. It's out there and it's being used. And on top of that, if we start to look into design practice, which is much harder to survey than the research literature, we also find that the rational method is either supported or permitted or actively recommended for use in design manuals all over the place. So if we go to the Alameda County Design Manual, again sticking with the Berkeley area, we'll see that the rational method is absolutely accepted as a way to design stormwater. Even here in Australia, where I think it's fair to say that the Australian Rainfall and Runoff Handbook's one of the snootier sort of publications or sets of design guidance, it grudgingly allows the use of the rational method. So it's certainly out there in practice and it's certainly out there in the research literature. So let's make sure that we're clear on this thing. So the first thing I want to point out is that it's predicting some sort of a flow, and this is our design peak flow, and that it turns out there's a lot of confusion about exactly what we mean by this design peak flow, and that confusion is largely embedded with the definition and how we think about what this runoff coefficient is. So before I go any further, I want to go through the fact that there seem to be at least 3 different flavors or interpretations of the rational method that are out there, each of which gives you a different interpretation of what this runoff coefficient should be, and most of which are thoroughly jumbled up in both design recommendations and the literature. So if we have a look at this runoff coefficient, its job obviously in this equation is to link rainfall intensity to flow. And we have these 3 flavors that exist. Now, the first of these is what you sometimes hear called the deterministic rational method. And this was one of the original purposes of the method's development back in the 1800s, was to deterministically make a prediction of a flow time series given a rainfall time series. And as you start to think about that, you see many, many problems with that, including the fact that the runoff coefficient should vary within the storm and sometimes should take values of greater than 1 and so on. But if we want to use it in this way, we would say that this runoff coefficient should be something like a ratio of the volume of flow produced to the rainfall volume that entered the catchment during the storm. We very rarely today see the deterministic rational method used. I think the last publication we found that used it was from 2005, but it's certainly an interpretation that exists. The next definition of the rational method, which incidentally is the one that the Australian Rainfall and Runoff Handbook promotes, is sometimes called the stochastic or statistical rational method. And this is a real little fudge factor of a method where what you're trying to do is to produce an estimate of the flow that has the same return period as the rainfall intensity with which you feed the method. And so in that situation, your runoff coefficient really loses a direct physical interpretation that you can sort of point at, and instead very much becomes a tuning parameter that tries to align the probability distributions of flow and rainfall. And there's very little, it's interesting to me that this is promoted, I guess, in our design manuals, because although it's obviously really appealing from a design point of view to be able to say, well, now I know the flow with the return period I specified precisely, there are very few places, especially in urban environments, where you have anything like the data you would need to work out what this runoff coefficient should be. So what we see really, I think, most commonly in use today is a version of the rational method that doesn't have a name. So we've been calling it the hybrid rational method. And in this situation, what you're trying to predict is the peak rate of flow given the average rainfall intensity for the storm given a particular return period. So this guy says, look, we know that we don't really know the statistics of the extremes of flow particularly well in most of these design situations. We have much more confidence in the rainfall. And so what we'll try to get is the worst case scenario flow-wise for a rainfall of a given return period. So firstly, there's very little out there that makes it clear that these three interpretations exist. So it takes a bit of digging and a lot of asking yourself if you have any idea what's going on to kind of land on these definitions. But I think what's worth being aware of if you're going to touch the rational method at all is that these different definitions lead to quite different values of what the runoff coefficient would be in an ideal world. And I think more problematically, that in practice and in research, these three methods are usually quite confused or at least not distinct from each other. So we had a look at this as well. We looked at the 200 most recent research papers that involved the rational method, and 50% of them didn't specify what runoff coefficient they were using, what its intention was. Many of them conflated a mass balance sort of definition, which is appropriate for this deterministic flavour of things, with the peak flow prediction in the rational method. So they were sort of mixing up their definitions. And of course, when you go to all of these many tables out there of runoff coefficient, you don't see any notification of actually what is trying to be produced by that runoff coefficient. So this is already a real quagmire of people using this simple method and quite what it means and quite what numbers should go into it. For the sake of us not being embedded in that particular quagmire, because we have other marshy terrain to get into, I will spend the rest of this talk focused on this hybrid rational method. So if I'm talking about a flow rate, I mean the worst case, the highest possible flow that would be produced given the rainfall conditions, given the design rainfall. So with these guys pinned down, because we'll look at the hybrid rational method, we then need to have a think about this contributing area. And of course, what this is getting us to is the fact that as a storm progresses, we see different parts of the catchment area contributing to flow. Now, an assumption in the use of the rational method most of the time is that at the time that peak flow occurs, you need all of your potential catchment area to be occurring. But of course, in practice, you can have complex shapes to your catchments that may invalidate that assumption. So overall, we start seeing that our contributing area is going to be some function of the hill slope size, the storm intensity and duration, and we need to think about landscape shape. Land cover can also come into this, but I won't dwell on that today. Last of all, we need to specify our design storm intensity. And here we need to summarise our rainfall for our given return period. And of course, here's where we start to hit, I think, the one clever thing about the rational method, which is that it acknowledges that storm length co-varies with storm intensity, and that somewhere along that curve, so this would again be our intensity, frequency, duration curve, but coming down just to an intensity duration line here and not worrying about frequency, that somewhere along one of these lines, we will find a storm duration and intensity that produces the greatest peak flow, given that we're on that line and we have specified and pinned down our return period. Again, this is nicely mapped in Australia. It's also quite accessible in the United States, often at the state level. And what we've been doing is saying that if we need to do some mathematics around this, because we obviously are sort of moving towards an optimization here, that we can lean on some of Dennis Koutsoyannis's work and summarize the intensity frequency curve as a ratio between two functions that specify how rainfall intensity varies as storms become more or less frequent, and also as the storm duration progresses. So getting out of the logarithmic scales that we saw in those other, in those Australian IFD curves, we would see that this relationship between intensity and duration has this sort of concave up shape. And what we're asking ourselves is, where along this curve do we need to apply the rational method? We need it to be at the place where we get the greatest flow. And again, traditionally, we've assumed that this will occur at the time of concentration, which is the first time, or the shortest storm duration rather, at which 100% of the catchment area would contribute flow. And this, again, is the conventional approximation that is embedded in design recommendations and standard application of this methodology. So time of concentration is in there somewhere. Now, this time of concentration is defined as the travel time from the furthest point in the catchment to the outlet. It's widely acknowledged that this is another of the big problems with the rational method, is that it's bloody hard to estimate what this time of concentration is meaningfully in any real catchment. And there's some, very disturbing pieces of work that have taken all of the design recommendations they could find for equations for the time of concentration and applied them to large numbers of catchments and just found orders of magnitude variation in time of concentration estimates. 500% type variations across watersheds, across equations for the same watershed. I'm not going to deal with that. I'm going to assume that I'm working in a perfectly prescribed model space where I can know what the time of concentration is perfectly. But we need to acknowledge this is another of the issues with this methodology. So what I think, though, is more problematic than can I find a good equation for the time of concentration is to ask the question whether this assumption that the time of concentration will always be the time that produces the maximum flow, is that a correct assumption? And this is a question that was put to me the first time I started teaching hydrology at Berkeley, and I hadn't thought about it particularly well before. So let's pause and acknowledge Sheila, who was the student in the class who asked this very good question. And we came back to this question from hydrology class in the studies I'm talking about here. So what we've wanted to do is to say, well, let's relax the idea of where we get the peak flow and say that there is some duration along this intensity duration curve that gives us that peak flow. And let's call that the critical duration, which may or may not be equal to the time of concentration. And obviously, finding what this critical duration would be is an optimization. So we can look at how the area, the contributing area, is changing with storm duration, and that gives us the dark green piecewise linear curve there. It's not necessarily truly piecewise linear, but if we make the assumption, the approximation, that runoff velocities are constant, it's not correct, but it's not too bad, then we get this piecewise linear thing. Then we've got our declining curve of the intensity duration, and then we look at their product and ask, where is this product maximized? That's giving us this critical duration. So our question really is, are these things the same? Is the time of concentration, the travel time to the outlet from the furthest point in the catchment, coincident with the critical duration that maximizes this peak flow? And this is a valid research question to ask. And of course, the answer is no, not necessarily. And I'll illustrate this with one case study around topographically non-planar hill slopes. And so we asked ourselves, how might hill slope shape affect this coincidence or lack thereof? And what we've compared are planar hill slopes, like I don't know if it's a parking lot or an airport or quite what we've got there in concrete, at the top, with either divergent or convergent hill slopes with some curvature on the bottom. And so if we go to this top case, and again, we've drawn a picture here that assumes a constant velocity, but if we allow for something more kinematic wave equationing, it doesn't actually change the result. In this situation, we do in fact find that the time of concentration is the critical duration, and we can use standard rational method assumptions with no worries. And this is really true across just about any shape of intensity duration curve that's in any way physically reasonable. On the other hand, what we often start to find, particularly with divergent hill slopes, such as this one at the bottom, is that as we allow the area to increase with increasing storm duration, we're adding on such small additional contributing area at the margin that our storm duration is extending and our intensities are dropping enormously, but we're not actually getting that much more flow contributed. And consequently, in these situations, we can start to see the critical duration diverge from the time of concentration. So the way that we dealt with this was to steal an idea from Peter Trock, who others will say maybe stole it from other people, and to represent hill slope curvature as a width function, and to allow that width function to vary exponentially up and down the hill slope. And if we do that, we're able to represent our curved hill slopes mostly by tuning the value of this A, which is sitting in the exponent that's telling us how this width is varying. So broadly, we've got divergent hill slopes where A is less than 0, and convergent, I've just said that backwards, I'm sorry, that's the 5 a.m. thing. Convergent hill slopes where A is less than 0, and divergent hill slopes where A is greater than 0. And these are just plots of how that width then varies with distance from divide. I don't like to present mathematics or derivations in talks, so I'll just say that we do some maths. But if we take these hill slope width approximations and merge them with a kinematic wave equation for overland flow, what we're able to do is to come out with analytical expressions for both the time of concentration and for the contributing area as a function of storm duration. And this lets us make analytical optimizations for the critical duration. And I'll just give you a quick aside there as to why we believe this bit of mathematics and model derivation for curved hill slopes, which, and this is just because it was fun, when you start designing your equations around really idealized mathematical shapes, you can of course go and make those shapes in the lab. And so Dana Lapides quite bravely and boldly went and learned how to do CNCing and assembled a whole lot of hill slopes with exponential width functions that were reasonably extreme by the standards we thought were out there, and then built her own rainfall simulator and used these to confirm that we were able to make good predictions and good differentiation of the flow behaviour based on the hill slope shape. So we felt pretty good about this. There's also been some par flow work, and I do need to pause and acknowledge folks at the lab who helped Dana out with getting par flow up and running. So a little connection back up to the lab with this work. With this mathematical approach, what we can start to do is ask what happens to the time of concentration and the critical duration as we take hill slopes with otherwise fixed area and fixed rainfall and change only the curvature. And what we find is that once we get a little bit past planar and our hill slopes start to become slightly divergent, we get this big drop off between the critical duration and the time of concentration. And if we push that through the other assumptions in the rational method, we can relate that to differences in the contributing area at the time of concentration versus the contributing area at the critical duration. We can do the same thing with the intensity, and then we can put them all together and say, well, what does this mean for the sorts of errors that we would get in our discharge if we use the conventional rational method versus a optimized rational method where we work out what this critical duration is. And what this is telling us is that in this particular case study on divergent slopes, errors in your design flow could be as large as 200% because of this assumption that's baked into the rational method that starts to fail given this hill slope morphology. I should emphasize that all of this has been done in situations that otherwise are well behaved as far as the rational method is concerned. So this has all been done for non-infiltrating hill slopes on which the kinematic wave equation applies, and small hill slopes. I think the overall area Danny used was a square kilometre. So this is very much still in the range of things for which the rational method is recommended for use. What we can then start to do is to extend that over a bunch of different return intervals and rainfall situations and start to ask, well, you know, do we at least sort of constrain our uncertainty by using the rational method? And it's quite hard to generalize this. And so what we've generalized are the ratios between the area at the time of concentration and the area at the critical duration, and the same thing for the rainfall intensity, where we've taken these ranges based on plugging realistic numbers into our equations. And really what we take home from this is that using the rational method does not offer a good way to constrain the uncertainty. What we've done here is say, well, if I were designing for the 100-year return interval and I happened to be on a hill slope with curvature such that my intensity ratio was 0.6 and my area ratio was 0.2, well, in that situation, I thought I was designing for the 100-year storm, but I've actually designed for the 1 in 10-year storm. And really, depending on how extreme these ratios are, you can pretty much fill out that space between 0 and the storm that you thought you were designing for. So there's a good space where things work out, but there's also a lot of uncertainty and a lot of risk if you don't understand how this optimization is working. So that's an illustration of how the timescales used in the conventional rational method can become problematic. A second area that's problematic is the runoff coefficient, and anybody who's taught or used the rational method will be familiar with the way that these runoff coefficients are usually treated as a constant. So anyone can do this, jump on Google, type in rational method runoff coefficient, and tables and tables and tables of numbers between 0 and 1 will start to flood your way. So these are just 2 examples, one from Queensland, one from New York State, just to show it's all over the world. When you start to think about this, this is a strange thing. And it's strange because when you say, okay, well, I expect these numbers to be less than 1. Why do I expect them to be less than 1? Well, partly because I expect some water to be detained on the land surface, these so-called initial losses, but also very much because I expect that some of my land surface is permeable and infiltration will take place. And of course, the key thing about infiltration is that it's not a fixed thing, but something that continues over time. So if we take the simplest sort of dumb model for infiltration, and that's very dumb, and say, well, it's approximated as a constant rate that's about the same as the saturated hydraulic conductivity, and then we think about what happens with storm duration, well, we would know that when we got to equilibrium, that is our whole catchment area is contributing, that then our flow rate would be given by the contributing area multiplying the rainfall intensity minus whatever that infiltration rate was. So this would be for a homogeneous area. And if we put that into the rational method, this must be equal to, so this is the peak flow rate, so this must be equal to the runoff coefficient multiplying the intensity multiplying the area. And so quite immediately, we see that the most basic mass balance here requires that the runoff coefficient depend on intensity, which in turn requires that it depends on the storm duration. And so here's another area where the duration dependence of the things that matter inside the rational method is usually approximated over. And so we thought this might be worthwhile investigating. When we investigated this, we used a slightly less done version of an infiltration equation. So we looked at this one, a sort of constant continuing loss assumption, but we said, look, what we think would be a more appropriate baseline case would be to use a Philip approximation so that we have some change in infiltration rate over time as well. And at this stage, things rapidly start getting pretty ugly. But one thing we can do is ask ourselves what would happen to the runoff coefficient as you change the storm duration for different assumptions. And this becomes quite dependent on the storm properties and the properties of the soil. So things rapidly start getting pretty nasty. In these 4 plots, before we look at what's on them, each column is representing 2 different IFD curve scenarios. So on the left, this smaller b value is telling you that the duration is dying off, the intensity is dying off more slowly as the storm duration increases. The larger b value says that this is a steeper descent. Then the rows here are looking at less and more permeable soils. And what we've done in each case is apply the Philip equation with different sorptivities. So if you want to just see the constant loss case, that's the light blue. So that could just be our case that is constant. The other 2 cases, we have a soil that was wetter to start with or less wet to start with in the darker blue. And we're asking what happens to the rational method runoff coefficient as you increase the duration of the storm that you're looking at. And what you see that's quite nice and gives you a little bit of confidence in using constant runoff coefficients is that actually once you get past durations of about 20 minutes or so, for most of these cases at least, that runoff coefficient is relatively constant. However, that's not true when we have the very steep IFD curves and the less permeable situation. And obviously, it's also less true when we have short duration storms. And this is slightly unfortunate because if we do turn to our design manuals and say, well, where is the rational method recommended for use? Well, the answer is small catchments without particularly permeable soils, and those are the conditions over which you're likely to have short durations. So there's sort of a bit of perversity in terms of recommendation versus behaviour here. Okay, so this is what's happening to these runoff coefficients in these simple models. The trouble is now that the fact that you can have a runoff coefficient that varies over time, this interacts with the problem of optimizing the timescale on your storm, and you start to end up with many, many pathways towards not picking the true peak flow, if I say the truth in this case is given by Philip-like loss. So we've got 2 different scenarios here. What we're showing in light blue is our truth case. So this is what we would predict and how we would optimize where we allow for the time-dependent infiltration. In dark blue, we now have constant loss rates, and in black, we have our constant runoff coefficient. And on each of those curves, I'm calling out the peaks or the assumed values that you would get if you decided to use different times of concentration. Of course, the time of concentration estimate also depends on the runoff coefficient, so everything gets pretty mucky pretty quickly. Without getting into it or trying to understand it in detail, the point is that you end up with many, many pathways to design flows that are not the quote-unquote true design flow. I don't really want to ask you to have to stare at these graphs and understand them. I think the story is there's lots of ways to get it wrong. And when we start to ask, well, how wrong is this? And now we're only looking at planar slopes, but we are varying climate, soil type, and how dry things are to start with, and trying out different sorts of assumptions that might go into the rational method. Really what you want to know is that anything in red, and particularly dark red, is looking at underestimates in the design flow. Anything in grey is looking at overestimates in the design flow with the rational method. And once again, we see that there's tremendous scope to think that you're using this method correctly, to be using it in a situation that is supposedly really what is recommended to be the situation where you use the rational method, and for these numbers just to be way, way out because of what's baked into the method itself. This is sort of where I want to pause and say, well, hang on, a chunk of that was me showing that we can end up over-predicting our design storms, and we can understand that we care if we under-predict them and everything floods. Here in Western Australia, we probably have the opposite problem most of the time, in that people are pretty conservative and are generally over-predicting flow. And of course, I shouldn't say of course, but like California, or like we think may happen in California, Western Australia is facing a drying climate that's likely to dry by probably another 15% or so over the next century. And we have very nonlinear responses of stream flow to reductions in rainfall. And at the same time, we're seeing all across our urban developments a heartening but somewhat cookie cutter approach towards installing water-sensitive urban design, which means lots and lots of biofilters and green retention basins and so on. These almost always come out of the land that's allocated as public open space in these housing developments. This has been a little concession to developers so that it doesn't have to occupy an otherwise profitable house site. And these things are huge and they don't fill up. They're oversized. And so we can see that what happens here is we've oversized our infrastructure, and there are quite large opportunity costs around aesthetic to start with, probably somewhat around capital works, certainly around maintenance, and almost certainly around function, because these things just never stay wet enough to actually do what it is that they're supposed to do. We don't get the vegetation growing. So, you know, if we only think about flood control, maybe we're not so worried about oversizing or over-predicting our design storms. But when we start to think about things like water-sensitive urban design, it does become more problematic. So we've been trying to help out a little bit around this problem, and at least around the curving slope problems, we've been working with Esri to add in a new tool for Arc Hydro. So Arc Hydro Hill Slope is in development and should be released fairly soon. We're actually just waiting on getting our papers around this finalised so that the product can come out at the same time as the publications. And what this tool is doing is automating the analysis of hill slope curvature and relating that to the overland flow hydraulic properties of things. So examples here, we've got an example from Walnut Gulch and an example from Reliance Creek in California. And what we can see there is a straight up classification of the subwatersheds in these basins based on their curvature. Are they headwater slopes? Are they convergent? Are they divergent? Are they more or less uniform? And sometimes, so our tool doesn't do a very good job when you've got a very curvy stream channel going through the middle of your subwatershed. And so you'll see some areas in dark grey there where there's large error in applying the methodology. So that it's not perfect, but it's not bad. What we can then do is take that curvature information and use that tool to make estimates about where there are large differences between the critical duration and the time of concentration, so that, for example, a user could apply this tool and come out and say, oh, gee, should I or should I not use the rational method in this area? This, of course, does rely on them. You'll see on the left-hand side that the x-axis is labelled with B, which is that parameter from the IFD curve. And so one of the things that this does rely on somewhat is users getting access to some fitted functions or some information about the shape of their IFD curves. If we're thinking about the runoff coefficient side of things, there's not really a good tool available to sort of wade through that quagmire of problems. But we have tried to pull out a decision tree that asks users to think about the climatic conditions, how the rainfall changes as storms become longer or shorter, what's happening with permeability, and whether we would be normally starting on dry soils or wet soils, and make some recommendations about maybe not using the rational method pretty strongly in some situations there, and certainly only using it with caution in others. But the conclusion I'd really like to leave you with is that this little method looks really nice, and certainly is appealing to those who are nervous of more complex models. But of course, we know that hydrology, even on small slopes, is quite complex, and the rational method is quite simple. And so making a simple method approximate the behavior of a complex system, your method might be simple, but deriving the numbers that then need to go in it then sort of have to suck up all of the complexity, and that's really not straightforward. And the whole situation leaves me sort of pulling these kinds of faces. I particularly like David Tennant's there, because it's quite evident that across a broad range of situations, conventional and recommended application of this method is going to lead to bad outcomes. And that's not because people have forgotten what they learned in their hydrology classes, but it's because we hadn't taken a really hard look at whether this method was internally consistent or sensible, and it actually isn't a lot of the time. So what do we do about that? And I find this very challenging, because I know that the students who leave my hydrology classes will be expected in their workplace to know what this rational method thing is and maybe expected to use it. But I sort of don't want to contribute to promulgating its use any further. I think probably we need to cut this guy off right about now. And it just continues to open up for me the questions around how do we better bridge what we are learning about as researchers with what's taking place in practice, and not in practice at the advanced end of water engineering, where I think there often is quite good integration between knowledge producers and knowledge users, but down in the humdrum every day, I'm designing a drain end of water engineering, where I think people probably do a lot of bad design, and I don't know that there are ways to pick up that that's happening, or to quantify the cost of that bad design, or to create a feedback back to the designers to create incentives to do better. And I'll just sort of finish with noting that that's really a problem here in Western Australia that I've become increasingly aware of since coming back, where the liability for bad stormwater is usually left with private landowners or local government, because the developers and the engineers who do the design pass on ownership of infrastructure after 2 years after construction. And so unless you happen to have your failure event in those first 2 years, you can pass on something that's really quite poorly designed, and somebody else owns that and somebody else has to pay for that. And so we have absolutely broken any kind of regulatory or governance feedback loop towards better engineering practice, which gives me a lot of disquiet about the state of the profession in some ways, and shouldn't be taken too blackly, because there's some awesome engineering practice out there. But again, at this not so good end, I think it's worth thinking about what we can do to shore that up. And possibly one way to do that would really be to say, actually, get the rational method out of your requirements and your acceptable ways to do design. So I'm going to leave it at that. Well, actually, I'll leave you with the papers that are out and on the way, and we're sort of at just about every possible stage imaginable of publication here. It's not easy to get something published about the rational method. I don't recommend it. But I do think it's been very useful, for me at least, in clarifying much of my understanding about this methodology that in many ways had been glossed over in my education, that I was probably continuing to produce fairly glossy educational material myself, and that now I personally want to think quite hard about how I handle in my teaching. So I've heard enough of me. You've probably heard enough of me too, and I'll stop.
Thank you, Sally. That was great. So you may unmute yourself and ask any questions you may have. I think that's the best way to go. I have a question. So when you tested this rational method and for divergent and convergent slopes, so did you consider like homogeneous precipitation?
Yeah, we did. And what we found was that our methodology, it in some ways you can think of it as an averaging methodology across the curves. And what you require to use that method is that things don't stray too far from a quasi 1D flow path. And of course, as soon as you get too much curvature, that is completely violated. So we were working always with pretty gentle curvature and worrying too much about how that curvature might affect things like rain angle or lead to inhomogeneity. It just was too gentle of a curvature for that to matter too much.
Sure.
Yeah.
Thanks, Michelle.
Thanks for your presentation, Sally. It was really nice to hear from you and nice to see you again. And so my question is regarding, your conclusions about barriers to communicating this. And so you mentioned the implications and liabilities from over-predicting and under-predicting. So I wonder what some of your recommendations could be, or if you have success stories on influencing this type of decision-making.
Yeah, I'm really thinking about it right now. I'd love to say I have a success story, but I'm feeling, I think it's going to be highly dependent upon the administrative setting that you're in, because if we look at, I'm not talking about the big stuff here, right? You need to get the operation of your big dams for flood control right, and that's very visible and very consequential, and experts get involved in that. And I'm very much down at the small end, the small biggies end. But I did mean to acknowledge right at the start here that there's been some work, particularly from Amir Agakushak's lab, trying to quantify the economic costs of nuisance flooding, and the conclusions were that things going wrong at this small scale are as costly to the United States as the sum of the catastrophic flood events, just because they're so much more frequent and they are not without cost. So I think there's a need to give some attention to this end of the spectrum, where I think, so I think things are really different depending on what administrative setting and what regulatory setting you find yourself in, who does own liability, who signs off on designs, whether you can actually build the thing you've designed. And I bet if you looked around and talked to local governments all around the United States, you would find places with some real success stories. I guess what I'm aware of right now is most urgently the things in Western Australia, and there's some obvious recommendations to make that include things like getting greater capacity to the local authorities to know what they're doing when they approve designs. Because right now what happens is developers come to the local government authority, they say, this is how I'm going to manage water. The local government engineer flicks through it. He's probably got 6 to look at in any one day, so he's got no time to actually think about any of them. He's probably got a general background in civil engineering, so he doesn't necessarily say, oh, look, I see some red flags that might be more hydrological in nature. He then approves it, at which point the local government has now assumed, liability for having approved that. And then it turns out somebody else in a different branch of the local government goes out and does the building approvals and building inspections and the permitting on the ground. There's not actually a way to ensure that what's approved is even what gets built. So, I mean, I can see, knowing my own process locally now in much more detail than I used to, that there's obvious places to change things. I think it would require an injection of resources, and I think the first step to getting that injection of resources would have to be quantifying the harm that's caused by over and under design, which is something that I don't have a dollar value for at my local area. I think it's not hard to do for flooding, but it's pretty hard to do for over design. You really have to think about what are the maintenance and opportunity costs. So yeah, I just sort of think it's been flying under the radar to a large extent because it's not dramatic. But I do also think it's the sort of thing where cumulative impacts might be much more dramatic than we think they are. Sorry, Michelle, that wasn't super helpful, was it?
Kieran.
G'day, Sal.
Hey, Kieran.
So let's say that, you convince people to abandon the rational method. Then, either they're going to, maybe, you can give them something, an improved rational method to be getting along with, or they're going to go to something else they know, the next level of complexity up in the hierarchy, that is widely accepted, widely understood, widely written into regulatory policies and guidelines, and that in some parts of the US at least is going to be it's going to be curve number and unit hydroref, TR55 sort of thing. Is that better? Is that an improvement?
You know that I've hated the curve number since Siva taught it to us back in Perth a million years ago, and therefore I won't ask that question. Look, I think the curve number type stuff, and correct me because I probably am wrong, I've mostly seen that used in more rural sort of settings, whereas I think in the urban settings that we were thinking about a bit more here, I suspect the curve number wouldn't be where you'd go next. I think you'd probably go,
wouldn't you?
Well, I would.
You'd think
I wouldn't necessarily be right.
That's entirely built on data from small rural watersheds in the Midwest would mainly be used for small rural watersheds, probably in the Midwest. In fact,
where are you seeing it used?
All over the place. Everywhere.
Yeah. I mean, it's everywhere in SWAT, of course, which is problematic. Yeah, I haven't benchmarked this against the alternative, and I think it's a valid question. Certainly, I don't think certainly in Western Australia, that would not be the alternative at this point. Something like swim would be the alternative, and the good folks are moving towards really complex urban models. Well, they tell me that this is good. I'm a bit, the complexity parameterization trade-off is not something that I think our urban engineers are across. They're sort of aware of it, but they don't really do much by way of uncertainty analysis. We have been looking at swim, so that's where I'm a bit more familiar with that, and that's coming from West Coast urban stormwater people, and I can't speak to what's going on in the Maryland area. Swim, I'd say, is better, but it's still problematic, and you start to pick up different problems, right? You start to pick up the problems of semi-distributed models with effective parameters, and stay tuned for hopefully the next publication from this group of people, which will be showing that those parameters really change their goodness of prediction as you do the things that you want urban models to predict, namely handle climate change or urbanization. I think we're in a difficult space. Modelling is hard, and look, here's the fundamental thing. Modelling is hard. These are supposed to be cheap and quick decisions to make. Resources don't go into thinking about how to do it well, and we don't know what the cost of failing to do that is. So it's been flying under the radar in many senses, I think. You tell me how bad the curve number is. I bet it's appalling. But you do that one, and then we'll write a big paper. It'll be great.
Well, it's already over an hour, so maybe any quick comment or thoughts. Otherwise, let's thank Sally for a great talk. And we have.
Sorry, Rebecca.
Yeah, we have a question from Rebecca, or comment. Okay, so Rebecca's she is saying modeling is magical. Yeah. So let's
look. I was so dismayed, Rebecca, when we did this. I thought, God, what do I teach my students now? Because the rational method's such a useful sort of thing to pull into the classroom, right? You have to get on top of IFD curves. You get them to think about some design. They predict a flow. You say, great, now design me a culvert. Fantastic, right? I think what I'm going to be replacing that with, as soon as I get off my bum and do it, will be analytical solutions to the 1D kinematic wave equation, which at least are physically based. And if you're going to be working over really small scales and mostly planar, mostly impervious surfaces, I think that's preferable. Oh, we exploded your head. Sorry. Yeah, but I think it's a valid question, and I've certainly had people say, oh, we should keep the rational method as a teaching tool, but I don't think we should if we don't think it should be used in practice. I don't think we should be teaching people, this is what my professor said, if we think it's wrong. Yeah.
Well, That's totally great. Yeah, so let's thank Sally. It was a great talk, and we'll see you some other time. Thank you.
I
Thank
hope
you,
so.
Sally. Really
Thanks,
great.
Sally.
Thanks for the invite, guys. It was lovely to see you all.
Bye.
I'm going to go find a hairbrush. Zero.